Hi, my name is Jimmy Lee. In this talk, I will present our work Spot SDC, which is a visualization system to help analyze a program's resiliency. This work is a collaboration between the University of Utah and Lawrence Livermore National Lab. We are becoming more and more reliant on high-performance computation platforms for all kinds of scientific discovery, such as weather and climate simulations, nuclear simulation, drug discovery, and machine learning. Our eagerness for the faster computation speed and large computation capacity motivate the industrial to design machines with smaller but more computation unit. This computation scaling has lasted for decades, and it is facing a challenge now. As the size of computation unit shrinks and the number of computation components increase in a machine, the applications running on these machines became more and more vulnerable to the errors, and the reliability of the computation results became a concern. There are different kinds of errors that can challenge an application's output reliability. Errors such as truncation error, position error, and hardware errors are noticed by the application domain and are well studied by the domain expert. Soft error is a special kind of error that has begun to threaten the computation's reliability. Soft error is special as it can occur randomly in a program's execution in any location at any time without notice. Most of the soft errors are caused by cosmetic particle strikes on the chips. The particle hits can switch the value of a transistor and lead to single bit flip events. The computation unit's scaling threats will make this problem worse in the future. Researchers have reported many soft error corruption events. In Oak Ridge National Laboratories, the supercomputer Dragas has a single bit flip events every 6 hours. The Q machine in Los Alamos has reported 26 errors per week. Amazon S3 data center is corrupted by a single bit flips, leading to the incorrect system states. After the corruptions, a large amount of servers start to sending each other the system's log information. Duplication technique is the common method to protect a program from silent error corruptions. Such technique includes instruction duplications, component redundancy, and process replications. They perform the same task at least twice and compare the result to detect whether a soft error corruption happens. This method will introduce a significant overhead if you want a full coverage of the protection of a program's execution. However, not all computation components are vulnerable to the soft errors. Some programs have some level of resiliency to the soft error, and the error happened during the computation can be mitigated. For example, a single bit flip happened in the programs such as K-means or Monte Carlo simulations won't affect the program's outcome a lot. For design an economy method to protect a program from soft errors, understand how programs react to the soft error is mandatory. In a high-performance computation program, a bit flip error can corrupt a pointer variable and cause a segmentation faults or a program crash. However, a program crash shows a clear symptoms, and the problem can be addressed by running the application again. A bit flip error can also mitigate by program because of program's natural resiliency to the error, and the program's final output is not affected. The most troubling outcome is silent data corruptions, which is an error corrupt a program's computation and the error propagate to the output without notifications. In this study, we use fault injection tool to simulate the effect of the soft errors by randomly flip the bits of the program and observe error propagation. The fault injection campaign is a collection of fault injection experiments. The result of a campaign is a collection of corrupt programs running logs and computation outcome. Usually, domain expert analyze these logs and gives us statistical profiles of a program's resiliency. Our visualization system is designed to analyze this log data, and our design is guided by the domain expert's analyze pipeline. Domain experts study different program components' SDC property and observe how error propagate in this component to infer or reason about their vulnerability. At the end, they decide whether this component should be protected and how to protect them based on the analyzed result. In this study, we use three matrices: SDC ratio, SDC impact, and SDC frequency to quantify a program component's vulnerability. SDC ratio tells how likely an error in a component will lead to SDC outcome. SDC impact shows how badly a SDC will introduce error into a computation's final output. SDC frequency gives the information of how frequently the SDC events happen in a program component. Study how error propagate around computation will help domain to understand why error explode or error are mitigated during a computation. These insights will help domain experts answer the question of why a program components are vulnerable to the soft errors and what may be the best way to protect a vulnerable component. In this work, we're checking error propagation by monitoring the critical data variables values. We define errors by comparing the error-free rounds with the error-corrupted rounds. In the visualization design, we utilize the natural hierarchical feature of our programs. The hierarchical visualization design enables users to examine a program's SDC property and observe how error propagates with the same hierarchical structures. This design will enable users to choose different granularity of a detail during the analysis as a program, functions, variables, or a line of code in both types of analysis. To summarize the result of the bit flip experiments, we designed a bit-level visual encoding, which refers to IG40 floating point format. This visual encoding enables users to study an individual bit's resiliency without losing a program's overview SDC profiles. This visualization here tells that in the conjugate gradient programs, for different variables and different lines, most of the bit flip happens in the mantissa bits won't affect the program's output. Majority of the silent error corruptions are caused by the bit flips in the exponent bits and the side bits. In the SDC property analysis and the propagation analysis, the source code correlation is important. As the domain experts find some interesting pattern during the analysis, they need to go back to the source code to reason about the patterns and find out why an error-corrupt program shows certain behaviors. The usability of the system can be demonstrated by a few use cases. One interesting resiliency feature of our program is how it reacts to the bit flips occurred in the time I mentioned. Here we can use our visualization to examine the impact of silent data corruptions over different computation iterations. From the result, we can tell that the impact of the bit flips will reduce with the increasing iteration numbers. This effect indicates that the soft error will have more impacts on the computation's early iteration than the later computation iterations. Fault injection can be randomly inject error into a program's computation. This stochastic process will introduce a problem that some program components do not have balanced sample coverage, and the resiliency conclusion about that will be problematic. Our system enables users to optimize the data online during the analysis. In this fault injection experiment with the fast Fourier transform programs, we see that line 725 does not cause any silent data corruptions in the initial data. Domain expert can make a conclusion that this line is resilient to the soft error. However, our visualization shows that the initial data has a bad sample coverage, that only a low mantissa bit had the samples. After optimizing the data with more samples are added to the component, the new data tell us that the exponent bits can lead to silent data corruptions. Such indirect data optimization operations will improve the fidelity of the analysis result. The spot SDC helps users to check error propagation in the case that error explodes or error is mitigated over time during the computation. Here we use the spot SDC to compare the SDC cases and mask cases in the conjugate gradient algorithm. In both cases, the errors start to explode or reduce in the same variable alpha, which is a variable to decide the search direction and whether the search direction is orthogonal with the previous search steps. This information indicates that the alpha can decide whether the conjugate gradient will converge or diverge, and it is an important variable that domain experts need to protect from soft error. With the feedback from our visualization, the majority of the SDC comes from the bit flip in the side bits, exponent bits, and higher mantissa bits. The sample from low mantissa bits does not offer too much information about the fault tolerance analysis, but they take large amount of sample in the fault injection campaign. This pattern indicates that the random sampling method wastes a large amount of computation resource on the useless information. This motivates us to propose a new sampling method to understand a program's resiliency. A simple optimized method can sample 80% of data from exponent and side bits and restore 20% from mantissa bits. A more sophisticated method can split the sampling process into 10 steps. In each sample steps, the algorithm used a binary search method to find the least significant bits that cause silent data corruptions. After the bit is founded, the rest of the sample will come from the significant bits to the side bit. We compare our two methods with random sampling method and use the SDC ratio and SDC impact to quantify the quality of the sample data. We use the fast Fourier transform and conjugate gradient benchmark to evaluate the performance of different sampling methods and compare it with the golden ground truth. The evaluation result indicates that both proposed sampling methods have better performance compared to the random sampling methods. The A with 2 sampling method is better to capture a program's SDC impact in both benchmark, and the iteration method had a small SDC ratio standard deviation compared to other methods. At the end, we summarize our main contribution as the conclusion of this work. We create a visualization tool that enables HPC domain expert to analyze the resiliency of the program. This tool provides multi-level of granularity details about programs' vulnerability to silent data corruptions. It introduces a new guideline for sampling the fault injection space and provides user a new insight about how error propagates through a program's computation.